All right, guys. Sorry I'm not in class today with you, but watch this video, go through it, try some of the problems or questions that I ask you, do some of the activities, etc., and hopefully you'll have time to start your homework at the end. So basically, today the objective is complex numbers. So this is the last lesson before we have a review and then a test. So realize we do have a test coming up. So basically, we're going to, first thing, gain some perspective of complex numbers by following the mini history lesson. So I just want to give you an idea a little bit, kind of the history behind complex numbers, where they came from. Maybe you've heard of them as imaginary numbers, and why they're called that. Would like you to recognize patterns by completing the cycle patterns and number activity. So as we get to that, I'll explain how that works. Connect the cycle of I by using what you learned from the cycle pattern. So what you learned from this pattern here, we're going to use it for imaginary numbers, and then use what you have learned by doing the homework. So basically, I'm not giving a lot of problems, sample problems here for you to do. The homework applies imaginary numbers i's and your radicals and your exponent rules and all that stuff all mixed together. So use what you know plus what you're learning about the complex number system, and the homework shouldn't be that big of a deal. So first thing, math duels. When I heard this, I thought it was pretty interesting. I don't know, I think back in the 1500s, early 1500s, how a mathematician became famous was they figured out something new in math that nobody knew, and they didn't tell anybody. What you would do is, if you came up with a way of solving a problem that nobody knew how to solve, is you would challenge another well-known mathematician to a math duel. And you would make problems and give it to them. They would make problems and give it to you. And whoever solved the most problems or whatever ends up becoming the winner. And the winner is the person who would be hired by the kings and queens and the wealthy people of that era to tutor their sons and daughters. So the way to make money and a name in math in the early, 13, 14, 1500s in that area, you found something new, didn't tell people too much about it, and did a math duel and became a tutor and made money, etc. So I thought that was kind of an interesting history part of the lesson. So here's an equation. Solve it. Take a little bit of time. How do you solve this equation? Well, typically I'm going to subtract 1 from both sides, and then to get rid of the x squared, we'll take the square root of both sides. So the square root of x squared is x, we know, and the square root of -1 is, and at this point in the history of math, this was an issue. They didn't know what the square root of -1 was. They had no idea. It didn't make sense to them. So, but what is this? So let's talk about this. Mathematicians had no answer for this problem until along came a guy named Cardano. Now, Cardano ends up solving this particular problem, x squared minus 10x plus 40 equals 0, and he solves it and says this is the solution, x plus or minus the square root of -15. Well, here's that negative inside the square root. How do mathematicians go about doing this? And he came up with some type of solution on how this worked. Pretty much everybody kind of laughed at him. Great mathematicians, they laughed at the solution, say, oh, you can't just start making up solutions, this imaginary solution. And this word imaginary stuck with a negative being inside the square root. So this is how we start talking about imaginary numbers if you've used them before. If not, you're in for a nice surprise here. Not until the early or late 1700s, 1777, a guy named Euler comes along. Now at this time, there are no such thing as math duels. The only way to become famous as a mathematician is find something new and let the entire world know about it as soon as possible. Well, he ends up taking this imaginary number I, and this is what he defines. He says I squared is equal to -1. This is the definition of an imaginary number. This imaginary number I, or complex numbers, we'll soon start to call it. Now to get I by itself, we take the square root of both sides. So the square root of I squared is I. And the square root of negative 1 is, we're just calling it the square root of negative 1. And again, this is what the imaginary number is. The square root of negative 1 is this I. So let's see how mathematicians actually use it. Here's our question that mathematicians couldn't solve. The x squared plus 1 equals 0. Subtract 1 from both sides. Take the square root. Square root of x squared is x. And the square root of negative 1 becomes this plus or minus I. Remember, when you take the square root of both sides, this needs to be plus or minus. This is a solution. They called it an imaginary because, remember, the mathematicians were joking about you can't just imagine numbers. And it kind of stuck. But this isn't an imaginary number. It's an actual number that we can use. They use it in electronics. They use it in, I don't know, suspension bridges, I think, various things. So here's another example. Let's take x squared plus 16 equals 0. To solve this, we want to find all the solutions that make that true. Again, subtract the negative 16 from both sides. Take the square root. Now what's the square root of 16? Square root of 16 is plus or minus 4. And what's the square root of a negative number? That's where the I comes in. So the square root of negative 16 is plus or minus 4i. So think of it. Pay attention to this part. The negative comes out of the square root as an I. Just like here. The negative came out of the square root as an I. So I look at square root of 16 is 4, and this negative comes out as an I. So this is one of the few mathematical discoveries that did not have a purpose. Actually, I think this is pretty interesting. Up until, well, throughout mathematical history, people would see something happening. And they're like, wow, how can we describe how that happened? Can we do something with it so we can make predictions on when it's going to happen again? Or can we stop it from happening? And this is where mathematics has really developed. Something happened, and people said if we can describe it in mathematics in numbers, then we can make a prediction as when it's going to happen again. And if we know the numbers, how it happens again, we can make those numbers change so it won't happen again, etc. So along comes this. I don't know if any of you guys have heard of the Tacoma Narrows Bridge. This is kind of interesting. I'm going to flip to the video here, and let's watch it.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
I mean, that whole bridge is rocking back and forth, and people didn't know why. They had no idea. I think it was doing this for several days. They had mathematicians, physicists filming it, studying it, and they needed to explain why is this happening, and if we can explain it mathematically, we can change the numbers to make sure it doesn't happen again.
Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing.
Pretty amazing, huh?
Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
So that's the video, but the concept or the idea behind that is for this Tacoma Narrows, it's something new, and mathematicians, people didn't know how to explain it. We don't want bridges doing this all the time, so they developed some new mathematics. Some people talk a little bit about harmonics and stuff, but I've read somewhere that more this aeroelastic flutter, this is what they call this aeroelastic flutter. Like if you took a piece of paper and lightly held it in both hands and then blew, how it would kind of flutter that way, and it developed a whole new math for it. So again, if we go back to this slide, the interesting part about this imaginary number I is this is something that came about just to solve a problem, but they had no use for it. There was no real, in the real world, Okay, great, we got this plus or minus 4i, but how do you use that as a solution to answer things? They had no use for it. And in math, that doesn't happen very often. There's only a few things in math that people developed, but there was no use for. Well, now we definitely have a use for it. All right, so here's what I'd like you to do. Here's a question that appears every so often on a SAT test. I want you to find the units digit. Now I'm going to stop right here. What is a units digit? Well, if I take a look at this number here, the units digit, this number 2 is the thousandths. This is the hundredths digit. This, whoops, go back one. This is the tens digit, and this is the ones digit. Or in other words, we can say it's the unit. A unit is 1. So I want to know, what is the units digit for 2 to the 57th power? All right, 2 to the 57th power. Whatever that number is, what is that units digit going to be? Now, if you can pause the video here, that would be great. Pause it and spend some time. Try to figure out how you can work this. Hopefully you took some time. It really will help you understand what's going on here a little bit. This is a difficult problem. If you tried your calculator doesn't have enough digits. It gives you some scientific notation that can't help you for anything. You can't find the units digit. So how do you go about doing it? So what I'd like you to do is you can go up to the substitute teacher, get the cycle of patterns of numbers activity, and do that and see if that kind of helps you out here. So good luck, have fun, and then when you're finished with that activity, you can watch the next video. But again, look on Canvas.